Hi, welcome to my channel. In this video, I am going to discuss about the kernelized SVMs. Suppose if you want to apply a second degree polynomial transformation to the two-dimensional training set. That means we are having the two-dimensional set. On this training set, we have to apply the second degree polynomial transformation. Then we have to train the linear support vector machine on the transformed training set. This is the process we have to apply linear SVM classification. Suppose if you want to apply a equation second degree polynomial function, okay, that mapping the function pi that you want to apply on the your data set. So here it shows the second degree polynomial equation or second degree polynomial mapping function pi of x equal to, here x contains two dimensional features, okay, two features, okay, pi of x1 and x2, that is mapped to x1 square root of 2 x1 x2 x2 square. Okay, these are the mapping function of the second degree polynomial equation. Now suppose here we are having the transformed vector is 3D instead of two-dimensional. Okay, two-dimensional. Now if you want to convert them into two vectors, so that means what happens, the couple of two vectors a and b is there. Okay, then if you apply this second degree polynomial mapping function and then compute the dot product of the transformed vectors. So here the equation shows that the second degree mapping function, kernel trick of the second degree polynomial mapping function. So that means pi of a transpose into pi of b. These are the two variables are there. They are the two variables are there. Okay, this is pi of a transpose pi of b equal to a1 square root of 2 a1 a2 a2 square transpose b1 square root of 2 into b1 b2 b2 square. On this data set we are applying, on this equation applying the dot product. So that means here a1 square into b1 square plus 2a1 b1 a2 b2 plus a2 square b2 square. So that is equal to a1 b1 plus a2 b2 whole square, that we can write in the form of a1 a2 transpose a1 a2 transpose into, okay, b1 b2 transpose, okay, whole square, sorry, a1 a2 transpose b1 b2 whole square, that is equal to a transpose b whole square. So it is the dot product of the transformed vectors is equal to the square of the dot product of the original vectors. So that is the difference. Okay, that is we are going to find out. So that the dot product of the transformed vector is equal to the square of the, okay, the dot product of the original vector. So that means a transpose b whole square pi of a transpose pi of b equal to a transpose b whole square. So here the key insights are, if you apply the transformation pi to all the training instances, then the dual problem will contain the dot product, that is pi of xi transpose pi of xj. Okay, if pi is the second degree polynomial transformation defined in the equation, okay, pi of x equal to pi of x1 x2 equal to x1 square root of 2 into x1 x2 x2 square. So then we can replace this dot product of transformed vector simply by xi transpose xj whole square. Okay, so you don't need to transform the training instance at all. Just replace the dot product by its square in the equation, like minimum of alpha 1 by 2 sigma I equal to 1 to m sigma j equal to 1 to m alpha power I alpha power j t power I t power j xi transpose xj minus sigma of I equal to 1 to m alpha power I, subject to the alpha power I is greater or equal to 0 for I equal to 1 to 3 and so on m. Now the result will be strictly the same as the if you had through the trouble of transforming the training set, then fitting a linear SVM algorithm. So but this trick makes the whole process much more computationally efficient. Then okay, then the function k of a comma b equal to a transpose b whole square is a second degree polynomial kernel. So in the machine learning, the kernel is the function capable of computing the dot product of pi of a transpose pi of b, okay, based on only the original vectors a and b. Okay, without having the compute the transformation of the pi value. So here it lists the some equation below equation shows the some of the most commonly used kernels like okay, linear kernel is there, that is a k of kernel k comma kernel k of a comma b equal to a transpose b. Okay, this is called as a linear kernel. And polynomial kernel equal to okay is a k of a comma b equal to gamma a transpose b plus r, okay, r of whole power d. Then Gaussian RBF kernel equal to k of a comma b equal to exponential of minus gamma into mod of norm of a minus b whole square. And sigmoid is one type of kernel is there, that is k of a comma b equal to tan h of gamma into a transpose b plus r. These are the different types of commonly used kernels in the machine learning. So here the equation below 7 shows the how to go from the dual solution to the primal solution in case of a linear SVM classifier. So, but if you apply the kernel trick, you end up with the equation that includes the pi of x power I. So, in fact, here a W cap, okay, W cap must have the same number of dimensions as pi of x power I. So, which may be huge number of or infinite numbers out there. Okay, so you cannot compute it. So, but how you can make the predictions without knowing the W cap? That is our problem. Okay, so here we can plug in the formula for the W cap from the equation 7 into the decision function for a new instance of x power n. So, and we get an equation with only the dot product between the input vectors. So, this make it possible using the kernel trick. So, the kernel trick is nothing but a, okay, here making the prediction with the kernelized SVM. So, that means h of W cap B cap, okay, pi of x power n equal to W cap transpose pi of x power n plus B cap. Now, that is equivalent to, if you substitute the value of W, okay, W transpose, that is equal to sigma equal to 1 to m alpha for I alpha cap of I plus into t power I pi of xi transpose, okay, into pi of x power n plus b cap. Now sigma I equal to 1 to m, okay, if you substitute this one, okay, if you come on this one, alpha cap of I into t of I into pi of xi transpose pi of x power n plus b cap. Now that is equivalent to sigma I equal to 1 to m alpha cap of I is greater than 0 at that time, alpha cap of I and t power I into k of xi comma x power n plus b cap. Okay, we can write this as a kernel. Okay, this is as a nothing but a one kernel. Okay, now so notice that here, since alpha power I is not equal to 0, only for the support vectors, making the predictions involves some computing the dot product of the new input vector x power n to only the support vectors. Okay, not all the training instances. Okay, now of course, if you need to use the same trick to compute the bias term B, okay, here we are using the kernel trick to compute the bias term B cap equal to 1 by ns, okay, sigma equal to 1 to m alpha cap of I is greater than 0, that into t power I minus w cap transpose into pi of x power I. Okay, that is equal to 1 by ns sigma I equal to 1 to m alpha cap of I is greater than 0 into t of I minus, okay, if you replace the w transpose here, okay, so that becomes the sigma equal to j equal to 1 to m alpha cap of I t power j into pi of xj whole transpose pi of xj. Now that is equal to 1 by ns into sigma I equal to 1 to m alpha cap of I is greater than 0 t power I minus sigma I j equal to 1 to m alpha cap of j is greater than 0. So that is equivalent to, okay, alpha cap of j t power j into k of x power I comma x power j. So like that we are going to find out replace the w value and b value with respect to some kernel values. So here the kernels are nothing but a linear kernel or linear kernel, RBF kernel, polynomial kernel, or Gaussian RBF kernel. Like that we are having the different types of kernels are there. All these things are we are going to apply to in order to find out the weight minimization of weight value and optimization of weight value and optimization of b value. So this is about the how we are going to kernelize the SVM. In the next video, I am going to discuss about the online SVM. Okay, if you have any queries or any questions are there, please leave them in the comment box. I will explain in the I can clarify your doubts in the next video. Thank you for watching our video. If you like the video, please subscribe my channel. Thank you.